Hi everyone, Nathan Yates here with the Tech Service Department. Welcome to our spring training. What we're going to do this year is talk about a couple of topics conceptually that will revolve around your spring startup, and then we're going to apply that to the actual equipment for a hands-on approach and how that's going to look in the field. So let's begin. Welcome to day one of our spring training. What we're going to cover today are four main topics that we get calls in to Tech Service on spring startup. So let's take a look at our agenda and see what we have going on today. The first thing that we're going to cover is how to test a reversing valve. The second thing we're going to look at is capacitor facts. The third thing is we're going to go over compressor diagnosis. And the final thing that we're going to look at is testing an ECM blower motor and how that looks out in the field. And throughout the presentation, if you have any questions that were to come up, feel free to submit those, and we're going to take a look at those at the end. So when testing a reversing valve, the main thing that I want you guys to grasp is what lines are what in heating and in cooling mode, and then how do you actually test the reversing valve to determine whether it's a good or a bad part. So the diagram that we have here is your refrigeration diagram for a heat pump in cooling mode. So what we have is our indoor coil, which is our evaporator, our outdoor coil, which is our condenser. We have our reversing valve, and then our compressor. The first thing that I want to drive home here is the common suction line on a heat pump. So the middle line that comes off your reversing valve, that is your common suction line that makes its way all the way back to the compressor on the suction side of the compressor. So that does not change at all. So this line is going to be your common suction in heat pump mode and in cooling mode. Now on our 13 and 14 SEER units, what you may see, for example, is our common suction line port, and you will need to hook in your low side hose on that port in order to read your suction side pressure. On our other pieces of equipment, we also do have a suction port as well. But especially on our 13 and 14 SEER, that port is how you're going to get your suction pressure reading. So again, the middle line coming off your reversing valve is going to be suction at all times, whether you're in heat or in cooling mode. Now, the discharge line that comes off your compressor, that is going to be thrown either to your outdoor coil or your indoor coil, depending on whether you're in cooling or in heating mode. Per our diagram here, we have it in cooling mode. So our discharge pressure coming off our compressor is going to our outdoor coil in cooling mode. Now, if we were to switch over to heat pump mode, our discharge pressure would be going into what would be this blue line. So this line would turn red, essentially, in heat pump mode, and we would be throwing hot gas into the indoor coil during heat pump mode operation. The biggest thing is that to know with our 13 and our 14 SEER units, this line is now your high side when checking your pressure. So this essentially is your discharge line in heat pump mode. It's important to know when testing a reversing valve, depending on what mode you're in. Now, some symptoms of a bad reversing valve would be the following. These are a couple things. So one, you'll have low head pressure, you'll have low compressor amp draw. Third thing is that your suction pressure is going to be higher, and you'll also have high discharge pressure. Now, just to add to that a little bit, your low head pressure portion of that would be is that if your reversing valve is stuck kind of in the middle, that discharge pressure that's coming off of the compressor is kind of going to be split, if you will. So half of it's going to go to one side of the valve, which will be your high side, and the other half of it's going to go to your low side portion of the valve. And that's why you can have a low head pressure and a high suction pressure when you hook gauges up to your system. Also too, on your amp draw portion of it, when you don't have that differential of pressure, you're basically cycling refrigerant right there at the reversing valve, and as a result, the compressor doesn't have to work as hard to pump, so you'll end up having a lower amp draw on that. Now, how do we test a reversing valve in the field? So This can be performed in heating or in cooling mode, so no matter whether you're summertime or wintertime, you can do it either way. Basically what you're going to do is you're going to take line temperatures right at the reversing valve. So you want to use a thermocouple type thermistor versus a laser, for example, to actually take these temperatures, because what you're dealing with is roughly about 2 to 4 degrees of temperature difference. So you want to be as accurate as you possibly can when looking at these temperatures. So first, what you'll do is you'll take your common suction line temperature, which again, if we look at a reversing valve, it's going to be our middle line here coming off our valve. So that'll be one spot that you'll take your line temperature. And again, you're always going to take your common suction line temperature, whether you're in heat or in cooling mode. Now, determining whether you're in heat or cooling mode, the second probe is going to go on one of your two outside lines here. And that'll determine whether, again, you're in heat or cool mode, because it's all based upon where your evaporator is. So in cooling mode, your evaporator is going to be your indoor coil, and in heat pump mode, your evaporator is your outdoor coil. So a real easy way to look at this is that one of these lines coming off the valve is going to go to your indoor coil, and the other line is going to go to your outdoor coil. So essentially, if you're in cooling mode and you want to test your reversing valve, you take your middle line temperature, and then you take the line that will be going to your indoor coil. What you're looking for under a good reading is roughly about 2 to 4 degrees of temperature difference. It can be as high as about 6 or so, but what I would consider normal is about 2 to 4 degrees. So if you're within that range, your valve is good, and we may need to look elsewhere as far as a problem goes. Like maybe we have an inefficient compressor or something like that that we need to diagnose. But 2 to 4, again, is what you're looking at for a good reversing valve. So now let's go take a look at a reversing valve on a unit. When it comes to troubleshooting a reversing valve, you want to make sure you use the proper tools to test the valve. You can either use a thermocouple type thermistor, or if you have a digital gauge set, you can use the clamp thermistors that would come with your digital gauges. So let's get into the unit and take a look at the valve. First thing that you want to do is unwire your condenser fan motor and then take the screws out to then take the top off. So let's do that. The first thing I want to point out to you guys is one, this line here is going to be our common suction line. It goes back to our compressor. Second thing is this is your discharge line here, and this part is a muffler, which often gets confused as a filter dryer, but this is just a muffler. And when it comes to your reversing valve, you'll have 3 lines that come off the bottom of the valve, and then you'll have your discharge line that comes on the top. Now again, this line runs through your muffler and back to your compressor. Your 3 lines coming off the valve will either go to your suction service port, which comes down over here. You'll have a line here that goes to your common suction port gauge hookup. So anytime that you connect to this line, you're always going to read suction pressure because that tracks back to the middle line on the reversing valve. And then what you'll have is another line coming off the other side of the valve, which essentially goes to your outdoor coil. So essentially, the easiest way to look at this is that you have one line that goes to the indoor coil, and then you have another line that goes to the outdoor coil. You will also have your common suction port hookup to read suction pressure in heat pump mode. Now, when it comes to placing your probes to test the reversing valve, you want to get as close to the valve as you can, because you're only dealing with a handful of degrees when testing your reversing valve. So what we're going to do here is we're going to use our thermal clamps from our digital gauge setup, and we're going to clip on to our common suction line. So this comes in through the bottom of the valve, and that's our middle line. And then per our test here, we're going to test this unit in cooling mode. So what we'll do is we'll take this line here, put our clamp amp on that. So again, this line goes out to your common suction port on the unit, and then what we'll do with our wires here, we're just going to feed this through where our refrigerant lines exit the unit. And then we'll re-hook into our gauges. Okay, so now we have our clamps installed. So again, we're going to measure our common suction line. And then since we're going to run the unit in cooling mode, we're going to check the line that goes to our evaporator coil. Now, if we were going to test this in heat pump mode, we would basically put our other clamp, this clamp here, we would have placed it on this line because your outdoor coil is your evaporator coil in heat pump mode. So we're going to run this unit in cooling mode and see what our reversing valve tests to. So let's get the top of the unit on and take a look. And now, with our condenser fan motor rewired in, let's run the unit and see what our reversing valve tests to. Let's take a look. So currently right now, what we're looking at is, let's call it 60 degrees on our STL line, and then on our liquid line temp line, we've got about 66. So we're within about that 7-degree range that we want to be at. It's a little bit cooler in this room, so our temperatures are a little bit farther away than what I would want. But basically, you want to be about 7 degrees on the differential on your reversing valve. Now, another thing you can keep in mind is when we were doing this test, I had to put the top of the unit back on, and that's mainly due to the fact that this is a good unit, and if I didn't put the lid back on with the condenser fan motor, the unit would go off on high head pressure. Now in the field, the symptoms that you would get for a bad reversing valve generally are going to be a suction pressure and a head pressure are going to be really close together. And you're really not going to be worried about going off on head pressure pretty quick. So when you're out in the field doing this test, just take the top off, leave it off, stick your probes in there on your common suction line, and then whatever line coming off the bottom on that reversing valve, whether you're going to be testing it in cooling mode or in heat pump mode, and take your temperature readings. Again, 7 degrees is about your max that you want to be at. If you're over that, we want to make sure that the test that we're performing is accurate as it can possibly be, that we're using thermocouples and not lasers to test the line temperatures, because you don't want to go through that whole process of changing a reversing valve and it not be a reversing valve. So with that, let's go into capacitor facts and see what we got. And the first thing that I want you guys to know about capacitors is, one, capacitors don't actually amplify the voltage. You can see a higher voltage across a capacitor, but this is due to the back EMF generated by the motor and not the actual capacitor. The second thing that we want to take a look at is, higher the capacitance, the higher the current on the start winding. The higher the MFD on the capacitor, the greater the stored energy and the greater the start winding amperage. Oversizing a capacitor can cause damage to a compressor or to a motor. So this is very important, that you want to make sure if you're replacing a capacitor, say on a condenser unit, you don't want to oversize that capacitor. So a couple things. One, Copeland does have an app that you can use to see what capacitors go with that certain type of compressor. You're also welcome to call into tech service and we can look up to see what capacitor goes with that unit. But the main thing is that you never want to oversize that capacitor for that compressor or that motor, because you'll end up damaging the windings on that motor or compressor. Third thing is that the voltage rating on the cap is what it can handle and not what it will produce. Meaning, you can replace a 370 volt rated capacitor with a 440 volt, but you can't replace a 440 volt with a 370 rated capacitor. Basically, you can't go down in voltage, but you can go up. So that's the other thing, is if you're replacing a capacitor and you're not sure which one to do, if you have a 440 volt capacitor, you can't go down to a 370, but if it's the other way around, you can. And the last thing that we're going to look at is testing a capacitor. So there's two ways that you can do this. The first way is that you can take all the wires off the capacitor and you can actually just de-energize the capacitor and then use your meter and test the microfarad reading on that capacitor by using the battery in your meter. The second thing is, which is really the more accurate way, is to test a capacitor when it's under load. So what you want to do is you want to measure the amps off the start winding coming off the capacitor, and you want to times that number by 2652. Then what you'll do is divide that by the voltage taken between the common and the Herm terminal on the capacitor. And now let's take a look at a map on what it would look like when you test a capacitor under load. So per our picture here, what I have is 2 meters. One meter is going to be testing voltage, the other meter is going to be testing the amp draw on the compressor. So first thing that you want to do is grab the compressor start wire that goes down to your Herm terminal on the capacitor. You want to take that amp draw. So per our example here, our amp draw is 7.8. So just you'll write that down, 7.8. And then the second thing that you'll want to do is take a voltage reading on your capacitor. And per our example, our voltage reading is 292.9 volts on our meter. Now, what you'll end up doing is taking your amp draw and you're going to times that by 2652, and then you'll take that number and divide it by your voltage. And that will end up giving you a more truer number of your MFD or your microfarad reading on your capacitor. So again, this is a more accurate way to test a capacitor under load, because what you're actually using for the voltage is the voltage coming right off the capacitor instead of, say, the 9-volt battery that might be in your meter, or maybe you might have a couple of AA or AAAs. So you're using a lot more voltage to get a more accurate reading on what the capacitor is actually giving you. Now let's take a look at a unit and see what it looks like in the field. Alright guys, so what I have here is a 14-SEER heat pump running in cooling mode. So let's take a look and see what this capacitor is reading out to under a loaded condition. So what you'll do first is just take a clamp amp meter. We're going to clip around our red wire here that's going to our Herm from our compressor. So right now we're reading, let's call it 3.8 amps on that. So when we come down to our equation here, we'll do 3.8 times 2652. And the next reading that we're going to take is our voltage reading on our capacitor. So we'll set up our meter here for AC volts, and we're going to check our common and our Herm terminal on our capacitor, and we're reading about 292, 293, let's call it 293. So we're reading 293 volts on our capacitor. Alright, so now we're going to do 293. So if we were to do the math on this, we're going to do 3.8 times 2652 divided by 293, and that's going to equal 34.39. So 34 MFD is what we're reading on this capacitor. Now on the capacitor that we have for this unit, it is a 35/5. So we are well within range on our microfarad reading for our cap. So your buffer zone on your capacitor is plus or minus 10%. So we're well within 10% of 35. So in this situation, our capacitor checks out good, and there would be no reason to replace it or anything like that. So with that, let's go right into compressor diagnosis. One key thing that you want to look at when diagnosing a compressor is the ohm values on the compressor. It's important to know which terminals are which and what resistance readings that you need to look for. This applies to your common, your start, and your run winding. When calling into tech service, we may ask for the ohm values on the compressor. When taking ohm readings, this needs to be performed on the compressor terminals and not the wires. The main reason for this is that we don't want to include the actual resistance readings of the wires in your overall value of taking ohms. You want to actually take the ohms directly on the compressor terminals themselves. Now, you may ask, well, what should my ohm values be? Well, this can be a little bit different on the compressor manufacturer and the actual model of the compressor. But say for single phase compressors, this answer in general can be found with the compressor manufacturer as far as what your ohms are going to be for that particular model. Now, some manufacturers actually have apps that you can download on your phone, or you can go to their website and look at the model number of the compressor, and that can tell you what the actual ohm values we need to be for that particular model number. Now, when it comes to your common start and run terminal on the compressor, we get questions in tech about this as well. So your lowest ohm reading is going to be between your common and your run terminal. So your run winding is going to be your lowest ohm value on your compressor. Your second value that's going to be higher than that is going to be your start winding. So your start winding is always going to be higher than your run winding when it comes to your ohm value. And then your third highest thing is going to be your resistance reading. That's going to include your run and your start terminal on the compressor. So you're actually going to be reading both windings together, and that's going to give you your highest reading. Now, just to reiterate that, again, your start winding is going to be higher than your run. Now, one thing I also want to point out here too is that a lot of guys like to use alligator clips to test the ohm values on a compressor. We kind of want you guys to stray away from that if you were to ask us in tech service, because what you really want is the needle points on your meter to make solid contact when you're checking ohm values on your compressor. And it all comes down to the overall connectivity of the actual meter lead instead of the alligator clip that you would maybe use out in the field. Because again, if you don't have a solid connection on your terminals, you may get a different reading depending on if you use your alligator clips versus if you just use your meter leads themselves on that. So with that being said, let's take a look at a compressor and see what that looks like. All right, guys, so what I got here is a Copeland scroll compressor, and then I also have a Copeland scroll that's also got a cutaway on it. But let's go ahead and ohm this compressor out and see what we got. So on our top terminal here, this is actually going to be our common. So if we go from our common to our run, let's see what we got. We got about a 0.9 for ohms. And now let's go over to our start. Got about a 1.8. And now let's go between our run and our start terminal, which should be our highest ohm value. And that's going to be 2.4, about 2.5 or so. So this compressor checks out okay. Now, if you were ohming a compressor to ground, basically what you would do, and again, you want to do that directly on these pins. So you'll pull the plug off the compressor, put 1 meter lead on each of the pins. The other meter lead can go just directly to copper as your ground, and then you'll just go to each terminal to ground. And what you want to see on your meter is OL when it comes to ohming these 3 pins out to ground. If you either read a number on your meter or 0, we've got a grounded compressor at that point. So when ohming those terminals out, that's kind of what you want to read under a good compressor. Now, let's take a look at troubleshooting an ECM blower motor. And the main 3 things that can take out an ECM motor are the following. The first thing is going to be related to line voltage. The max line voltage that you would want to have, say, on an air handler is 253 volts. I usually tell guys 250 is your max, so it gives you a little bit of a buffer zone on that. But 253 is the max voltage that you would want to see, say, on an air handler for an ECM blower motor. The second thing is going to be related to moisture. This is going to be really easy when it comes to troubleshooting because you're either going to have water or you're not going to have water in your blower compartment Now, when it comes to water, the main thing is if you were to come up on a unit that's installed horizontally, you just want to make sure that that unit is installed at least level, or if not pitched forward a little bit, so any water and condensation that would be produced by the evaporator coil in cooling mode can drain effectively out into your drain system. The third thing is going to be static pressure. Now, when it comes to static pressure, this directly reflects the performance of your system and your overall CFM output to your registers. Now, the higher your static pressure, the lower your CFM output is going to be. So in turn, like for example, on the variable speed setup, that blower motor, if you were to have a higher static, is going to have to work harder in order to push the CFM output that you have selected for that install. So if it's got to work a lot harder in order to push that CFM for an extended period of time, it may prematurely go out on you, mainly due to a high static pressure. So if we were to have a motor failure on, say, a furnace or an air handler, how do we test it? Well, what you can do is you can use our Broad Ocean motor tester. And what this will do is that this will help eliminate whether or not you have a board or a motor problem. So with the tester, it's powered by 24 volts by the blower board. And then you'll also have a green light that will indicate the horsepower on the motor. So simply put, if the motor runs when using the motor tester, we need to troubleshoot the board, and we may need a new board from our distributor. If the motor doesn't run when we use the tester, then we need to replace the blower motor in that furnace or air handler. So now let's take a look at a piece of equipment and how this will look in the field. So what we have here is our Broad Ocean motor tester. It's going to say Broad Ocean right on it. This is the tester that we tell you guys to use to troubleshoot our fixed and variable speed blower motors that you will find in our air handlers and our furnaces. So when you get the tester, you're going to have 3 different adapters that are going to come with this tester. So for our example today, we're working on a G7 furnace, so we're going to use this adapter here. So basically all you do is you take your adapter, plug it into the tester, and then you'll just tighten down these screws here. All right, and then you'll have your Molex plug on the other side. And what you'll do with this guy is take your blower motor plug off your blower board. Now this again is 24 volts, low voltage, and it's going to plug right into the tester. You hear a little click, it goes in one way. And then your 2 wires coming off the bottom of your tester is where you're going to tag 24 volts. So on our particular furnace, we have a variable speed setup. So I'm going to tag the R and the C terminal off this blower board. Put this on here. All right. And this is what will power our tester. So once you apply power to the tester, you'll have a red LED power light that'll come on. And then once you turn the tester on, meaning turning the blower on, you'll have a green LED along the bottom here that will tell you what the horsepower is of the blower motor we're testing. So for our example, we've got a 1/2 horsepower motor that we're testing. So right now I have the selector switch on low, and if I were to go to high, that blower motor is going to ramp up a little bit. And then if we go back down to low, that blower motor is going to ramp back down. And then if we go to off, the blower motor is going to shut completely off, and then we lose our green LED to determine what horsepower motor it is. So this is a really handy tool to determine whether or not you may have a motor issue or a board. And just remember that the tester essentially takes the place of the board. So if the motor runs with your tester, your motor's just fine, and we would need to look elsewhere for troubleshooting. And again, that's how we test our ECM blower motors on our furnaces and air handlers. And let's take a look at the questions that have been submitted, and feel free to go ahead and submit more questions as we go along.